Welcome to the seventh lecture of course module Communication Engineering. So in the previous lectures, we have seen how to do the multi-tone modulation. Okay. And we have already seen what is the power requirement of EM signal in the case of multi-tone modulation. What is modulation efficiency? Now in this lecture, I am going to talk about how to generate the AM signal. Okay, how this conventional AM signal can be generated. Okay, so that we have to look at. So I am going to tell you one of the very popular method, you can say, which is our square law modulator. So let's begin the discussion. So in the case of generation of AM signal, okay, conventional AM signal, using the square law modulator, we have to concentrate upon this particular block diagram. Okay, so this block diagram can be implemented in the circuit form. Okay, and then we can generate our corresponding conventional AM signal. So now, first of all, you can see, as I said, that we should have a certain message signal, and then we need to have a certain carrier signal. Okay, the sinusoidal carrier signal of high frequency. So in the case of square law modulator, in this case, what we have to do is, first of all, we have to take the message signal and carrier signal, and we have to add them together to get a signal B1T. Okay, we have to implement a circuit that will be able to add them together and to get the output equals to V1T, which will be the summation of the two. Fine. So after getting this output V1T, this output V1T should be applied to a non-linear device. Okay. So the readily available non-linear device that can be used for this purpose is our any general purpose diode. Okay. Any general purpose diode can be used. So we already know its VI characteristics of the any general purpose diode. So if we write the current voltage equations, then that equation current through the Zener diode will be like any normal diode will be equals to ID equals to saturation current I naught. Then it will be in bracket e to the power some exponential factor, okay, V upon eta Vt minus 1. So generally for the approximation purpose, we generally neglecting the minus 1 term. So what we can understand that this VI characteristics of the diode is nothing but following the exponential law. Okay, it is an exponential curve. Okay, so in a certain range of this particular exponential curve, what we can do is we can write the exponential series. As we know that if we have an exponential series Ex, then that can be written as x plus x square upon 2, then x plus x cubed by 3, okay, and so on. So that way it can be written. Fine. So we can write the exponential series. So basically what we are interested in this case is we are interested in the first two terms of the exponential series. Okay. So there will be a certain factor. Okay. So there will be a certain factor that will be equals to A, and then we will be having VIT. Okay, this is the input voltage, and plus B and VI square T. Okay, so these two factors will be the factors that will be related to our exponential expansion. Okay, now after having these factors, we also have a certain higher order factors. So generally we are not interested in those factors in its mathematical form, because that will be going to be neglected. That we have to see how it will be neglected. So basically those terms are going to be neglected. Okay, so we have to concentrate upon these two factors mainly. Okay, because this two factor is going to give you the relevant means conventional AM form. Okay, relevant conventional AM form. So that we have to look at. So basically we need to have a nonlinear device. If its input voltage is known, then it should have a characteristics in which the V output of this particular nonlinear device should be following this particular mathematical expressions: A VIT plus B VI square T. So any general purpose diode can serve this purpose. Okay, so in this case, what we can see is, first of all, we have to take the masses signal and the carrier signal. So as I said, we will be taking the MT. Okay, here I'm not telling you that whether a MT is a single tone or a multi-tone. Okay, we can generalize first and then even we can go for the separate analysis. Okay, so that can be done later on. So first we are taking the masses signal and then we are considering the carrier equals to AC cos 2 pi FCT. Now this two signal has to be added together by this summer. Okay, so the output will be V1T. So our output will be equals to MT plus AC cos 2 pi FCT. Now this V1T is going to be applied to a non-linear device. Okay, and after having this non-linear device, what we can do is in this non-linear device, the input signal will be V1T and the output I am denoting it as V2T. So now this V2T is equals to A V1T plus B V1 square T, because this non-linear device should have this particular characteristics. Okay. So now if you substitute this V1T into this expression, okay, we can further expand this V2T. So that is equals to AMT plus AAC cos 2 pi FCT, okay, because A is to be multiplied in this V1T, and then we have to square this V1T. So we are going to get M square T plus AC square cos square 2 pi FCT plus 2AC MT cos 2 pi FCT. Okay, now the bracket will be closed. This factor B is going to be multiplied over here. Now after getting this V2T, okay, we have to just rearrange all these factors. Okay, I'm just going to rearrange all these factors in such a way that we will be able to exactly see a certain factor available in this expression, which is similar to our conventional AM case. Okay, so that we have to look at. So if we search for, we can see that here we have in this case, okay, we are going to get one of the term which is 2AC MT cos 2 pi FCT. Okay, so our massive signal is actually being multiplied at this certain portion. Okay, and here we have another carrier signal. So as we know that in the case of conventional AM, this carrier signal has to be added with the product of the carrier signal with the mass signal. Okay, this is what the actual form. Okay, if you see all the previous standard equation. Okay, so what we can have is I can just take these two terms together. Okay, after multiplying this B inside this bracket, so we can take this two terms together and we can keep all other terms separately. Okay, so if we keep these two terms together, you can see that we have AAC and then cos 2 pi FCT as the common. Okay, we can take out this as a common. So here I will be getting a factor equals to 1. This factor is equals to 1 plus here you can see we have multiplied B inside and AC is now out. So this is becoming 2B divided by A, because A is not available here. So this A is going to be in the denominator multiplied with MT and then cos 2 pi FCT. Okay, so this is what we are going to get. Okay, after keeping this two term together and then taking the common AAC cos 2 pi FCT plus I can write now AMT and then plus B M square T. Okay, this term, and then we can write BAC square cos square 2 pi FCT. And now from this equation V2T, what we can see is this particular equation. Okay, up to this section you can see just particular this section. Okay, this can be like rewritten as AC square AC dash. Okay, this can be written because it is AAC is written, so A is a certain factor, it is a constant value for a particular modulator. So AAC you can rewrite like AC dash, and this 2B upon A can be written as KA. Okay, as we already know that Ka is nothing but our amplitude sensitivity of the modulator. Okay, Ka. So this is nothing but our Ka and Ka multiplied with the MT. So here we can see that this particular factor is nothing but our conventional AM expression. Okay, and the rest of the part is some extra terms that we need to be filter out. Okay, we need to filter out them. Fine. So basically we have to filter out them by having a band pass filter. Okay, we need to have a band pass filter so that these other terms can be filtered out. Okay, so to get that, basically here I am just writing after passing through the band pass filter. Here we can see that the band pass filter will have a certain central frequency, and that central frequency should be equals to carrier frequency f equals to fc, and then it will have a certain pass band. Okay, so it will be centralized around central frequency fc, and then it will be having a certain pass band, so that this entire signal should be allowed to pass. Okay, and rest of the signal should be filtered out. So why it is rest of the signal will be filtered out? Because here we can see that AMT is nothing but our massive signal, and it will be consist of a low frequency component. So this is a low frequency component signal. Again, we are having Bm square T. Again, I will show you that it is also having a certain significant frequency component that need to be filtered out. Okay, what will be the maximum frequency component? I will tell you now. And again, you can see we are having BAC square cos square 2 pi FCT. So when you expand this cos square 2 pi FCT, then we are going to get frequency component at f equals to 2fc. Okay, if you expand this like 1 plus cos 4 pi fct divided by 2, so here it is going to give you one DC term, and it is going to give you one sinusoidal term at frequency f equals to 2fc. So basically we have to choose a certain band pass filter of a certain pass band characteristic, so that only this portion should be allowed through the filter, and all other frequency component should be rejected. So I will tell you in the next slide what kind of spectrum this particular equation V to T is going to have. Okay, you remember this equation. This is very important equation. So I will tell you what is the filter Fourier spectrum of this particular equation. We can get the Fourier spectrum of this equation, and we can plot it. So you can do that analysis, like you can calculate the Fourier transform of this equation, and then you can plot the Fourier spectrum. So I have not calculated Fourier spectrum, Fourier transform, but we can directly plot the Fourier spectrum by just seeing its frequency components. Okay, so I will do that in the next slide. So after passing through the band pass filter of a certain pass band, we are going to reject all other components, and we'll just pass or we'll just retain this particular component. So after passing through the band pass filter, we are going to get V output T, that will be AAC 1 plus 2B upon AMT cos 2 pi FCT. So basically it is nothing but V output T can be written as AC dash plus AC dash. This AAC is written as AC dash in bracket 1 plus, you can write this as a KAMT cos 2 pi FCT. Okay, so that MT can be single tone case, or it can be multi-tone case. Okay, so that is nothing but our conventional AM expression. Fine. So here I have written directly for multi-tone single tone case. I have taken MT equals to AM cos 2 pi FMT. So here we know that Ka multiplied. What is Ka here? So that you please remember, K is nothing but 2B upon A. Okay, K is nothing but 2B upon A. It is our amplitude sensitivity of the square law modulator, whose unit will be inverse of the voltage. Okay, if it is a voltage expression. Fine. So basically this equation will be mu equals to, we know that we have already defined modulation index, mu equals to Ka AM. So it can be further written as AC dash 1 plus mu cos 2 pi FMT into cos 2 pi FCT. So I hope up to this point it must be clear. Okay, it must be clear. Now we have to consider one thing, that this can be also written for just a multi-tone case, like we can keep it simply empty, rather taking MT equals to EM cos 2 pi FMT. Okay, so that can also be written. So obviously again it is the equation of conventional AM only. Fine, whether it is MT or MT equals to a certain singleton modulated signal. So now if we have let us suppose MT, then we have to understand one concept, that if MT equals to AM cos 2 pi FMT, let us suppose, okay, then from this expression, okay, this expression, you can see the V to T expression that we have. So in this expression, we can see we are having a term M square T. Okay, so we have to understand if we have any frequency, any signal whose frequency is cos 2 pi FMT, its frequency was FMT, then what will be the spectrum of a signal which is M square T. Okay, so if we square this signal, okay, we are just considering this particular case when MT equals to AM cos 2 pi FMT. So when it is M square T, you can just square this signal. We are going to get AM square cos square 2 pi FMT. That will be equals to AM square 1 plus cos 2 pi 2 FMT divided by 2. Okay, so basically it is going to give you one DC factor, okay, one DC term, okay, and one frequency component at f equals to 2fm. Okay, that you remember. So basically when it is consist of maximum frequency component equals to fm, then m square t is directly proportional to, or it consists of a frequency component f equals to 2fm when we are squaring it. Okay, you can generalize these things like if you are making like m cube t. Okay, if you make it m cube t, in that case this signal is going to consist of frequency component proportional to f equals to 3fm. Okay, similarly you can, if you make it m to the power 4t, it is consist of a frequency term proportional to 4fm. So what I can generalize is, so whenever I am making a power of n, okay, if we raise the power with factor of n of any known message signal mt, then there will be a certain term which is going to be proportional to nfm. Okay, so the maximum frequency component that we are going to get in the signal is nfm with all other terms. Okay, there will be a certain other terms, but the maximum frequency component of interest will be of nfm. So that we have to understand. It is very basic concept, very good concept that we have to understand, because many of the time in the communication you will find that we are going to like raise the power of the message signal or any signal, and then it will be asked that what is the expected spectrum of the signal. Okay, so here we can easily understand that if we are squaring it, it will be multiplied with the factor of 2. So maximum frequency component is going to be 2fm. If it was earlier it is fm, then obviously if mt is having its maximum frequency equals to fm, then m square t is having its maximum frequency equals to 2fm. Similarly, if it is raised by a factor of n, then the maximum frequency component will become nfm. So why I'm telling this all? Because we have in this expression bn square t and bac square cos square 2 pi fct. Okay, so here I told you that it is containing a frequency component at f equals to 2fc, and here it is containing because if we are considering mt to be a multitone signal, okay, then obviously if this multitone signal is having its maximum frequency equals to fm, then m square t will consist the maximum frequency component that will be equals to 2fm. Okay, so this is what the idea is while plotting the spectrum for this particular expression v2t. So we can go on calculating the Fourier spectrum. Okay, you please try to do this by calculating the Fourier transform of this equation by considering that mt is having its Fourier transform equals to mf in the case of multitone modulation, and then you can plot this one. Okay, you can separately plot this one also, okay, by just considering it to be a single tone modulation. Okay, so that you can do, and you can do the analysis. So I'm just plotting for the case of multitone signal, considering mt is a multitone signal. So here you can see that first of all we need to plot this, okay, and then we need to plot these things. Okay, so what we have is, you can see that first of all we have in this expression the message signal itself, okay, amt. So let us suppose that is this mt is having its Fourier spectrum equals to fm. Okay, it is denoted by mf. Okay, so basically this particular portion, okay, I have just written that you just try to understand this one. This blue curve is denoting the Fourier spectrum or frequency spectrum of signal mt. Okay, I have not written here, but it is corresponding to signal mt. Okay, so I have just plotted here. Okay, it is from minus fm to plus fm because it is a multitone signal. Now for m square t, here you can see we are having m square t term. Okay, so some factor a is multiplied, so please do not bother about what will be the magnitude. If you do the exact calculation, you will be able to write the magnitude portion also. Okay, but yet I have not defined it. Okay, so you can define it and then you can plot it accordingly. Okay, and as I explained you that please do not bother about the shapes. Okay, because I am taking number of times a triangular shape. Okay, then you may be confused why it is always triangular. It may or may not be triangular, it can be something else. Okay, but just for the simplification of explanations, okay, I'm just taking the this triangular shape. Okay, so you can take any other shape also. Okay, so just I'm not showing the magnitude anywhere. Okay, I have not shown the magnitude, I'm just interested in the frequency part. Okay, so this is for our mt. Now for m square t, we have this m square t term. So as I said, with this explanation, the maximum frequency component is going to be the twice of MT. Okay, so here I have plotted this. It is maximum frequency component is going to be twice of the FM. Okay, again it is going to be at up to -2 FM. So please again do not bother about the shape. Okay, it can be anything else. Okay, it can be anything else. So we are going to get m square t. Okay, similarly, as I said that due to squaring of the signal, there may be a chances that we are going to get a DC term. Okay, so one DC term may be appear at this center. Okay, one more DC term may appear at this center. Now we have this BAC square cos square 2 pi FCT. Okay, so again it is going to give you one impulse function, as we know that for the cosine we are going to get the two impulse function, one at f equals to 2fc, another at f equals to -2fc. Okay, and it is going to give you one DC term again. Okay, so all the DC terms will be added together and it is going to give a one particular impulse at frequency f equals to 0. So at this point we are going to get the addition of the several DC terms. Okay, and now we are going to get one impulse at f equals to 2fc. Similarly, another impulse at f equals to -2fc. Fine. So now we can see this portion. Okay, this is nothing but our conventional AM signal. So we already know that in the conventional AM signal, if any message signal MT is having its Fourier spectrum equals to MF, then that spectrum is going to be shifted around the carrier frequency FC. Okay, this is already known to us. So what I did is I have taken the carrier frequency at this FC, and then around this MF signal is being shifted. So it is consist of a portion of FC plus FM, and FC minus FM. Similarly, it is the same mirror image has been plotted in this side, negative frequency side. Okay. So I hope you must be able to follow this spectrum. This spectrum is very, very important, okay, to understand. So once we have this spectrum of our V2T signal, okay, after the nonlinear device, okay, what we have to do is we have to pass this signal through a bandpass filter. So let us suppose we have a bandpass filter with characteristics like this. Okay, so we are having this bandpass filter characteristics. So once we have this bandpass filter characteristics, what we can see is only this portion of the signal is allowed to pass because it is lying inside the passband of the bandpass filter. Obviously, the characteristics that I have plotted here for the bandpass filtering is ideal characteristics. Okay, practically we do not have this type of characteristics. There will be a certain roll-off factor. Okay, and it will be not like a steep fall, but there will be a gradual fall you will find. Okay, there will be a certain transition band. Okay, a certain transition band you will find. There will be a gradual fall. Okay, so now here you can see that we have taken the ideal low pass filter characteristics. So the filter has been taken such a way that only required frequency component will be selected and all other frequency component will be rejected. Okay, so this all portion will be rejected. It is going to be rejected by the filter. Okay, so after passing through this filter, we are going to retain only these frequency components, which are equals to or same as the required frequency spectrum for conventional AM. Okay, so this is what our need. Okay, this is what our need. So that's why we need our one band pass filter to filter out all rest of the signals. Okay, similarly, you can consider even if we have the higher order terms, all other higher order terms will be maybe again filter out. Okay, so that we can take care of. So basically, we are considering this type of characteristics of the nonlinear device. So after having this one more constraint that we have to look at is because we are choosing a bandpass filter, okay, to select a certain portion of the this particular frequency spectrum to get the conventional AM signal, we have to make sure that there should be no overlapping between the spectrum of M square T and the spectrum of this conventional AM. Okay, here we can see that this spectrum portion, okay, this spectrum, the lowest portion of this particular component is coming at FC minus FM. Okay, and here it is, its maximum value is coming at 2 FM. Okay, so for the proper generation of the conventional AM signal using the square law modulator, there should be a certain finite gap between them. Okay, so what I mean to say that if there is no finite gap or there is an overlap between the spectrum, then this band pass filter could not separate out this particular conventional AM signal. Okay, so there should be no overlap between these spectrums. Okay, this portion and this portion. Okay, so how this can be make sure that there should be no overlap? By having this particular condition, means this frequency minus this frequency, should this the difference between this frequency and this frequency should be greater than or equals to 0. Okay, so it will be good if it is greater than 0. Otherwise, if it is equals to 0, we need to have a like ideal band pass filter. Okay, so it should be at least greater than 0. Okay, this difference between the FC minus FM minus 2 FM should be greater than 0 to make sure that these two spectrums are not overlapping. Okay, if it is overlapping, then there will be a impossibility that we cannot generate the a conventional AM signal using square law method. So basically this gives rise to, if we consider FC minus FM minus 2 FM greater than equals to 0, then this FC, the carrier frequency, should be greater than 3 FM. Okay, should be greater than 3 FM. Okay, this is the basic condition. So you remember that equal sign only will be suggestive if we are having the ideal low pass filter. Okay, if we ideal band pass filter. If we don't have ideal band pass filter, this FC should be greater than 3 FM. This is the necessity or necessary condition, you can say, for generation of the conventional AM using the square law method. Now the same signal can again be demodulated once we have generated the EM signal in the practical scenario. Okay, we can again demodulate the same signal. Okay, we can go for the demodulation of the same signal by again having the same square law demodulator. Okay, so now we have to see, as we have seen in this equation. Okay, again you remember this is same expression. So while demodulating, okay, I have just rewritten this expression over here. Okay, AC dash in the expanded form. So our VAM expression was AC dash cos 2 pi FCT plus AC dash KAMT cos 2 pi FCT. Okay, so this is our expression. So this expression will be radiated and then it will be received by the receiver antenna, and now it is has to go through the demodulation process. So again, how this can be demodulated using this square law demodulator? Again, we are going to have a nonlinear device of the same characteristics. Okay, like V2T, which is having A VMT plus B VAM square T. Okay, of similar characteristics. Okay, it is of same nature. Okay, same nonlinear devices we can use. So once we are going to use the same characteristics of a nonlinear device, when we apply the same signal again, we are going to get the V2T. Okay, so this V2T, if you apply to this particular nonlinear device, then again, following this particular equation, we are going to get this expression. Okay, you can easily find this expression. Okay, so once you will find this expression, okay, in the case of generation, we had used the band pass filter, but in case of demodulation, we have to use a low pass filter. Okay, because we know that our massive signal is our baseband signals. Okay, it is containing the significant low frequency component, and therefore we need to have a low pass filter to demodulate this particular signal. Okay, so if you see, you can easily verify this equation number 2 by just substituting this VMT into this expression of V2T. Okay, so after having this expression, you can see that in this expression itself, we are having lots of terms. Like one term is at frequency F equals to FC. Okay, another term which is a product term between MT and cos 2 pi FCT. Okay, here we are going to get another cos square 2 pi FCT term, which is nothing but a frequency component at F equals to 2 FC, and then we are going to get M square T terms, okay, multiplied with cos square 2 pi FCT. Okay, so cos square 2 pi FCT is going to give you one frequency term at DC and another one term at DC and another frequency term at F equals to 2 FC. Okay, and then again we are going to get MT cos square 2 pi FCT. Okay, so basically what I am trying to say is in this entire expression, okay, this is not containing message. Okay, this portion is do containing message. Okay, but it is shifted version around the carrier frequency FC. Okay, MT multiplied with the cos 2 pi FCT. So this spectrum of MT is being shifted around the carrier frequency FC. Okay, now this expression again not containing any message signal. Okay, but here we can see that in this case we are going to get instead of getting the massive signal empty, but we are going to get the m square t. Okay, we are going to get m square t because this expression is going to give you 1 plus cos 2 4 pi fct divided by 2. Okay, so basically this term is going to give you this particular term. Just try to means understand this. Bac dash square plus k square m square t factor by 2. Okay, after expanding this one. Okay, so this factor we are going to get. Okay, because it is again a low frequency component. Even if we are having maximum frequency component in empty equals to fm, then n square t will be consist of just double of that fm. Okay, we have to take care of that because I will tell you now. So basically this is one of the component. Okay, and then this is going to give you another component which is actually containing the massive signal, because again this term is going to give you 1 plus cos 4 pi fct divided by 2. So because of factor 1 by 2, we are going to get this component, okay, which is nothing but 2b, like 2 and 2 will be cancelled out in this case. So we are going to get BAC dash square KAMT, okay. So basically this two term is going to give you the message part and m square t part, okay. And rest of the terms should have been rejected by the low pass filter because they are all the high frequency component. You remember that all the other component will be rejected because we are passing through the low pass filter. The low pass filter is going to reject all higher frequency component because it is at fc. It is again this frequency component is around fc. Okay, so these are all high frequency component. It is going to give you one dc component plus this component at 2fc. So this all things will be rejected. This dc component will be blocked by the dc blocking capacitors. Okay, similarly here again this cos 4 pi fct term is going to be rejected. Okay, so only the term which has left out is these two terms. Okay, after the low pass filter, so basically what I am saying is, as I said, that this MT is having this Fourier spectrum and its m square t is going to have this type of Fourier spectrum. Okay, so all other spectrum is at higher frequencies. Okay, it will be at available will be at it will be available at or higher frequencies, higher order frequencies. Okay, and those will be cancelled out or rejected by the low pass filter because it is not falling within the pass band. It is falling in the stop band of the low pass filter. Okay, so here it is the stop band. Okay, only this is our pass band. So within the pass band only this spectrum is falling. Okay, this spectrum is falling. Now we can see that while passing this while applying this low pass filter, we are not only passing the signal empty, but we are also passing the signal the certain portion of the signal m square t, because m square t is also starting from right from the zero and it is going like this, and then a certain portion is also passed through the low pass filter. Okay, a certain portion of the m square t is also passed through the low pass filter. It is not only passing the signal mt, but it is also passing a certain portion of the signal n square t. You must be thinking that n square t is having its maximum frequency component is 2fm, then why it is passing? No, it is a multi-tone signal and therefore its a spectrum consists of frequency between 0 to 2fm. Okay, so up to a pass band, if its pass band is lying somewhere here, up to this pass band, all the frequency component available in the m square t will also be passed through the low pass filter together with this frequency component of mt. Okay, so all this frequency component will be passed up to this point, and after that all this portion will be rejected. So basically what I'm saying is our desired term, okay, the desired signal or desired massive signal that we want to extract is empty. It is not m square t. Remember that we had sent the massive signal is equals to empty, but because of the generation method, okay, or you can say because of the demodulation process, we are going to get this particular term m square t, which is a not desired term. Okay, so basically because this term is not desired because it is not our actual message signal, our actual message signal is empty, and therefore I am calling this particular term as a noise component. Okay, this entire factor I am calling it as a noise component. Okay, because it is going to give you some unwanted added signal into your desired signal component. Okay, so because of this, we need to have a certain condition. Okay, what is this condition is, so if I'm calling this as a noise component, if I'm calling this as a signal component, then if we calculate the signal component to the noise component, okay, you can easily verify this expression. I can substitute this signal component and noise component. You will be going to get 2 upon KAMT. So if this factor 2 upon KAMT is much larger than unity, then only a reliable reception of the message signal could take place. You remember that. This is very important condition in which we are using the square law demodulator. Okay, so if once we have done the square law modulation, okay, it is not necessary that we have to go for the square law demodulation only. I'm just telling you one of the method of demodulation of the AM signal using the square law demodulator. But we have to follow this certain condition. If it is satisfying this condition, 2 upon KAMT is much larger than unity, it means that the signal component is much larger than this noise component. And therefore, whenever we are receiving the signal quality will not degrade much. Okay, it will not be degraded much. The signal will be available and we will be able to reliably get the information or message signal, whatever we have sent from the receiver side, from the transmitter side. So please remember this expression. Okay, this can also be further analyzed for MT equals to a single tone case like AM cos 2 pi FMT. So here you know that MT equals to, when you substitute uh, AM cos 2 pi FMT, then cos 2 pi FMT is taking its maximum value equals to 1. Then Ka into AM is multiplying, then it is giving you modulation index mu. So it will be becoming like 2 upon mu. Okay, 2 upon mu for the case of multi-tone single tone signal. So I hope this discussion how to generate the AM signal using the square law modulator and how to demodulate this signal again using the square law demodulator must be clear. Okay, so please try to convince yourself that you have understood the concept. You please go through once again whatever I have explained. Okay, so in the next coming lectures, I will be telling you the demodulation process of conventional AM signal using one of the most popular method and practically used in our radio systems is our envelope detection. Okay, it is the most simplest circuit. Okay, so I will tell you that envelope detection of our conventional AM signal, okay, in the coming lectures. So please stay connected, and if you have any doubt regarding this lecture, please drop me a message in the comment box. So please, thank you for watching. Stay connected for the coming lectures. Thank you.